So now the second part of the lecture, I want to do more examples with Bernoulli's equation and some applications of Bernoulli's equation. The first application that we're going to look at is for free jets. So consider a tank, like shown in the sketch, that is open at the bottom. We're giving a few geometrical measures there. There's the diameter of the opening at the bottom. There is the total height of liquid from the surface to the opening, and another height there just to a given point of reference. So we're going to consider this situation, and we're going to apply Bernoulli's equation here. Well, first of all, we're going to get the velocity at v at the point here, this velocity. So there's a jet of liquid of diameter d flowing from this opening shown with a velocity v. So we have a point 1 at the surface and a point 2 at the jet. And so in point 1, we are at the water surface. And as indicated by our little triangle there, this is at atmospheric pressure. It also has no velocity. At this point. Point 1 is just sitting there in the surface. So we're going to consider a streamline that goes all the way from 1, where the velocity is 0, and that streamline sort of accelerates slowly until the maximum velocity here at the jet. Point 2 is at the jet. This is a free jet. Free jet, and so it's open to the atmosphere. And again, so this is also at atmospheric pressure. But the velocity is, of course, different than 0 there. So we want to find that velocity. So V1, basically, at point 1 is approximately 0. It's close enough to 0 that we can use that. And between 1 and 2, all we have is a change in elevation. So we have gamma h. H is that height between 1 and 2. Has to be equal to, so all we have at point 1, sorry, at all that we have is the elevation being converted to dynamic pressure, basically. Both static pressures are atmospheric. So rho h equals 1/2 rho v squared. P1 equals P2, C2 equals 0. We put our Z coordinates starting from there, so Z2 equals to 0. And so it's kind of like a free fall sort of interpretation there. And then there's a point down here at 5 that is a little further below. And so between 1 and 5, we have, again, P equal to 0, P5 equal to 0. It's all at atmospheric pressure. It's a free jet. And so we have velocity at 5 is equal to square root of 2g. We just did this a little while ago. And there's a big H here and a little h there. I hope you can see that. It's not small, it's not too small. Okay. So what we're saying is that, well, this is V5. So what we're saying is that velocity continues to increase. As the jet free falls. Just like a free fall in gravity. Now the same result, well, this is a very classic, of course, result from physics, from really fundamental physics, basic physics. But as an exercise, try to obtain, you can see that the same result can be obtained using Bernoulli between three and 2. 3 being right there at the bottom. Okay, and do this as an exercise. The interpretation that we can have from this result over here between 1 and 2 is that basically all the fluid elements' potential energy gets turned into kinetic energy as they go from the surface to the exit of the tank. This is a very straightforward application. If no questions, I would like to go to the next. Is everyone okay? Okay. The next one is a sharp exit. So now we're looking at some sort of sharp exit right next, like shown in this sketch, on the side of a big tank or something. We have a sharp exit. Yes? It's still a free jet in the sense that we have atmospheric pressure here. Now you perhaps remember from your physics class as well that when you have a sharp exit in a liquid, we observe this phenomenon which is called vena contracta, which is an effect it's due to the fact that the fluid in here cannot really turn this sharp exit quickly, and therefore the diameter dj, the diameter of the jet, is smaller than the diameter of the hole, say. The jet sort of contracts. So we have curved streamlines over here. And the pressure is not constant. There's an acceleration. We haven't proved it, but there's an acceleration, and so the pressure is not constant. Just want to give you some physical description of this first. So P1 and P3 is equal to 0. But in fact, due to this curved streamlines and the contraction of the jet, P2 is actually not 0. We're not going to develop this any further. I just want to give you some physical description of the phenomenon that happens here called vena contracta, which you might be familiar with, but just to remind ourselves. And there's always a contraction coefficient which, say, called C, is equal to AJ, the jet, divided by the area of the opening. This depends on the geometry of the opening. And it's a type of thing that you find in handbooks available, the contraction coefficient, and later on we're going to look at also the losses that are associated to these types of devices. So we have several typical geometries that one could find for this situation of an opening. So let me just show you some options here. And again, like I was saying, these are situations where you find a handbook. Mechanical engineering handbook will have all this information available for solving problems. And you can have something like a completely sharp knife edge opening, and this has been determined to have a contraction coefficient of 0.6 approximately, and this is the ratio between the area of the jet and the area of the opening, and so it's the ratio between the diameters squared. If you have a very rounded, nicely rounded exit, then there won't be this effect of vena contracta, and you will in fact have a contraction coefficient equal to 1. If you have a sharp, what's called a re-entrant opening, like shown in this picture, so it's sharp in here, then that increases the contraction coefficient to 0.5. So obviously, if the diameter contracts here, the jet is a little faster than it would be if the diameter is larger, because of conservation of mass. So these are the sort of geometries for this problem. We won't discuss it any further. Yes. Same fluid everywhere, and same, say, tank with the same pressure or depth of fluid in the tank. This would be, the whole tank would be on the left side. Yes, this is depends on it's just, we're not looking at surface tension effects here. Surface tension effects are completely neglected in this whole discussion. This is just the sort of dynamic effect of the fluid not being able to turn the sharp corner and adapting, because this is now moving at speed. That's the situation of a jet. So let's look at the application of Bernoulli's equation in the case of confined flows. And here, the typical situation that we will have is that we have to apply both Bernoulli and continuity together for these types of problems. Continuity meaning conservation of mass. And so consider in this case a fluid in the tube in which the inlet area, A1, is, so here as shown in this diagram, A1 is equal to 2 times, is double A2. So inlet area twice outlet. Because of conservation of mass, then of course we must have, so consider steady flow. So there's a fixed rate of volume flow into and out of this piece of pipe. And so the mass flow rate, which is m dot equals to rho times the volume flow rate. Usually we use Q for volume flow rate. The rate of volume flow Q is fixed. The mass flow is also fixed. So m dot equals rho Q is equal to, of course, a constant. And what is the mass volume, say, for example, through any area? The volume of fluid through any area suppose in a time unit, in time delta t, is going to be the velocity times the area times delta t, because if a fluid moves this distance in a unit of time, this distance will be velocity times delta t. And if I multiply that by the area, that is going to give me the volume. So the volume of fluid passing through any area is going to be velocity times area times delta t, where this velocity is sort of an average.
So is that Q?
That is Q. Well, Q is actually flow rate, so Q is that per divided by time. Yeah. So Q is actually this divided by time. So it's always V times A. Mass conservation or continuity, m dot equals rho VA equals constant, and so this, for this case of a confined flow, is simply that V1A1 equals to V2A2. This should be no surprise. We've already discussed the conservation of mass for a control volume, and basically we can look at this pipe as a control volume, and this is the simplest form of 1D steady conservation of mass. So we are going to use, of course this is assuming incompressible, right? So rho 1 is equal to rho 2. In the case illustrated, of course, we have the ratios between the areas, and so we would apply this relation that was given in this example, and we get V2, the velocity here has to be equal to twice the velocity at the opening. And we can use that with Bernoulli's equation. In many applications, we'll have to do just that. Confined flows. Other applications of Bernoulli equations are for flow rate measurement. So we are going to consider, in the ideal approximation, ideal flows. We neglect all effects of viscosity or compressibility effects. And so the basic idea of flow rate measurement, these are the different types of flow rate measurements that we have. This is called the orifice plate. This is called a nozzle. This is a venturi. So basically what we're doing is putting an obstruction in the flow inside a pipe, just putting an obstruction there. And so this restriction in the pipe allows us to measure now the pressure differences and between a high velocity and a low velocity area. So first we place a restriction in the flow. Then we measure pressure differences. Between a point 1 and a point 2, where point 1 is at 1 would be at a higher pressure and lower velocity because of Bernoulli, of course, and 2 would be at a low pressure and higher velocity because it's forced to go through this restriction. So continuity means that the velocity has to be higher. Bernoulli says pressure has to be lower, and so assuming that the flow is horizontal, so Z1 equal to Z2 always, to make it easy, flow is horizontal. And we can apply Bernoulli between these 2 points 1 and 2, P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Assume uniform velocities through sections 1 and 2. These are all sort of sweeping assumptions. Of course, the velocity is not uniform, but in an engineering approximation, we're happy to consider it. And so there's always a degree of approximation here. Q is equal to A1 V1 equal to A2 V2. This is a confined flow, like in the previous slide. A1, the volumetric flow rate is constant, mass flow rate is constant, and also density is constant. And so we can combine these two to get a measure of the flow rate. This is what we want to measure, right? The flow rate. So the flow rate is Q, and basically A2 V2, and I can obtain V2 from the other equation. And let me just write it down and see if it makes sense to everyone. Square root 2 P1 minus P2 and rho, and we have 1 minus. We did a similar calculation some time ago in an example. But I just want to point out that the important, the thing that I want to point out is that Q is actually proportional to the square root of delta P. This is the important conclusion that I want to point out, which is that the flow rate can be measured by looking at pressure differences. Yes?
Just in the denominator,
A2, or I'm sorry, this must be a typo, is A2 over A1. Just trying to speak and write at the same time. I made a typo there. Yes, another question. Oh, okay, thank you. Thanks very much for catching that. So flow rate can be determined by pressure differences, and this is what we use in the lab. And these are devices which are very common, and you know, commercially can find the orifice plate volume rate meter. You find them, you can buy them, and they give you specific. We are assuming here that they're ideal, but in the real case, there will be a small loss, and now the commercially available devices will actually tell you how much that small loss, so that you can make more precise calculations. In the ideal approximation, we can find the flow rate measurement just by looking at the pressures and knowing the difference in area between the opening and the rest of the pipe. But in a real case, we can adjust this a little bit to account for losses. As we look down through this catalog of devices, we have the greater losses in the orifice plates and the smaller losses in the Venturi. But the Venturi one is more difficult to construct and so on, so it will be more expensive. In an application in engineering, you will have to weigh all those decisions. see if those little losses are acceptable for a for a lower investment price or not. That's the decisions you're going to have to make. But in the end, we will use a differential manometer or some pressure device to conclude about the flow meter, the flow rate in the pipe. This is a direct application of Bernoulli's equation. So these are sort of typical applications that we discuss that are basic applications of Bernoulli's equation. And I want to introduce, before we finish today, the energy equation. And we will discuss this quite a bit. Now, the energy equation is probably the most important equation that you will have to deal with as mechanical engineers. And you will see how some of the examples we bring to the lecture will be very important in terms of design decisions that you may make. So recall that from the first law of thermodynamics, we simply have that if we look at the change of energy with respect to time in, say, a system, this is going to be equal to the flow, the time rate of heat transfer plus the rate of work done. This is our... How many of you are taking thermo at the same time as this course? Well, most of you. Who's not taking thermo? Just to know. Okay. 1, 2, 3, 4. 5? No? Okay. So, but surely you must have seen just the first law of thermodynamics in high school, so you might be comfortable with just the concept that any change of energy has to be due to flow of heat and work being done in a system, right? So this is what we're trying to say here. The total increase of stored energy, so basically the rate of increase of total stored energy in a system has to be equal to the rate of heat transfer plus the net time rate of work done on the system. So let's write the energy in terms of a intensive property, which is energy per unit mass. And so I'm going to call that little e, and that's going to be the total stored energy per unit mass. So this term here on the left is, I can write as ddt integral of this little e times rho d volume, rho density of the fluid. And that's going to have to be in our energy equation. So this is the net rate of heat transfer. So if we have heat coming in minus heat going out, that's going to be the net heat transfer. And we could also have work in and work out. Oops, that's a little bit sloppy. Let me do that again. We could also have work out. For the energy per unit mass, we write this as U plus V squared over 2 plus GZ. So we separate the energy terms into what is called the internal energy, the kinetic energy, and the potential energy. but all of these per unit mass. And so now what we want to do is write the energy equation for a control volume per unit mass. So when I apply the partial derivative of this whole net total stored energy, as you may recall from the discussion in the conservation of momentum, and as I said then, I'm not going to do the full mathematical derivation, but it should be intuitive that I am applying the derivative of a sort of product here, so I will get a basically the total change of energy in a control volume will be the change of energy inside the control volume with respect to time plus the flow rate of energy through the control surfaces, like we had for the case of momentum. So I'm going to write this term so I'm going to, I think I should clear these. I'm going to take a snapshot in case anybody has doubts, and clear these annotations and write again that I'm going to consider the change of energy net in a control volume as the change, the partial with respect to time of the energy in the control volume, rho dV, plus the contributions of flux across any control surfaces. So control surface, and we have the flux of energy due to the fact that there's movement of fluid, right? So fluid is coming in or out of our control volume. Control volume is fixed, remember, a black box, and as the fluid goes in with a certain velocity, for example, we could have one inlet, one outlet, the simplest case, then it carries with it energy. And so that term is the flux of energy, V dot N dA. So that's the total change of energy, and this has to be equal to the Q net in and W work net in, the net addition of work in the system in the control volume to be proper. I'm looking at the control volume now. Net. That's why I've added the little word net. So it would be the difference between what goes in and goes out. I just called it net. So put them both together. So this Q dot net in is the sum of Q in minus Q out. In is positive, out is negative, so the net in maintains the positive sign. If I get a negative sign, it's actually going out. I still use the words net in, but if it's negative, it's not really in. The sign will tell me. Yes? This is the unit normal, as we had for the momentum equation. It's the same form of that we had for the momentum equation. It indicates that there is energy going in with the fluid to a control volume, there's energy going out with the fluid, and there could be a change of total energy in the system, like with the mass and the momentum equation, the same point of view. Outward, normal to the surface. Unit vector. So, as always, we're going to want to choose our control volume wisely so that we can have a very simple expression for that. We want to choose our control surfaces to be perpendicular to the velocity. For example, that's the first thing what we want to do. And so we have our, this is the energy equation. This is the total in the, for our control volume. And what we're going to do is look at the different sort of terms that could come in. Many times we're going to, in the fluid mechanics course, many times we're going to forget about the heat. We're not going to worry very much with heat in our systems, unless it's sort of a given. But we are going to worry a lot about work. And what we're usually going to be dealing with is systems where we turn energy of the fluid into work, or turn work into giving energy to the fluid. That's what we're going to be dealing with. Either one. So what we want to discuss is the forms that these heat and work terms take for a fluid system. So very quickly, the forms of heat transfer, and like I said, we're not going to often deal with this, but we could have radiation, we could have conduction, or we could have convection, but more importantly, we will deal with work. So what are the forms of work? We could have what we call shaft work, which is in an axis of any rotating device, turbines or pumps, fans, propellers, and so on. We have that the work in those cases is equal to the torque at the shaft times the angular velocity. Of the axis or shaft of the turbine or pump, and this is torque. That's going to be our measure of work in that case. Then we could have pressure work for a fluid, and for this consider that force is equal to pressure times area, right? So suppose that we have, we're looking just a little pipe, and there's fluid in here. So I'm going to look at pressure being applied in this area, and suppose that the fluid is moving such that I have this line moving to this new position here. And so we want to look at what the work was. Work, you remember, is force times velocity. So this is equal to force times dx dt. So in this case, we're going to look at, so suppose we have a small differential of work because we've moved this just a little small distance. Pressure work. That's pressure times the differential of area times the normal velocity. So force times velocity, remember, work is force times velocity. And velocity normal times the area, I can write like we have done before using a dot product between the velocity and the normal, unit normal, outward normal. And so now that's the small work unit. I could get the total work done by pressure by integrating this. And so the total work done by pressure is equal to the integral across any controlled surfaces of minus P V dot N dA. And the final form of work that we may have is the work due to shear stresses. In a fluid, although many times we will neglect it in the inviscid approximation, but if we had tangential forces, we could have a small unit of work due to shear, and this would be some sort of tangential force times velocity. But with our usual approach of always selecting the control surface to be perpendicular to the velocity, then the tangential force is always going to be 0, and so we don't have to worry about this term, which is very useful. So see control surfaces perpendicular to velocity, and this term is 0. But this one is going to be important. The work due to pressure in the fluid. And this one also for any rotary devices, which we will often have. So the final energy equation, we can now rewrite in terms of, perhaps we're going to just leave a Q dot for the heat, and many times it won't appear, but now we have two different important forms of work to put on that right-hand side of the equation. So the lecture time is coming to an end. You have to go to your next lecture. What we're going to do next class is see the energy equation in applications and do at least 3 examples, classical examples of energy equation. Where? Sorry? Force times velocity. I'm just simplifying things here. Oh, W dot. Yeah.